occupied room today, but it's densely packed in pockets. Weirdly, it's sort of strange. How many of you took the midterm that was just in here? It's just about half a dozen of you. How'd it go? Okay, well, I guess best not to ask jokes or tell jokes about midterm. Anyway, I hope it went well. Anyway, happy Friday. We're continuing on our excursion down random variables and expected value. And here we have a problem, as we usually do. Sum of two dice. Okay, so you roll two dice and add them together. What's the expected value? Put in terms that we've been using. X1 and X2 are the results of the two dice. We can add them together and form another variable X. What's the expected value? Okay, there are two ways of approaching this problem. One is the good way and one is the bad way. I'm going to show you the bad way first. Okay, so just so that you know what the bad way looks like. And the good way is the way you should always approach this problem, all right? So, but first, the bad way. The bad way is, by writing out the PDF for this. Okay, so we know how X should behave. The range is 2 through 12, and we can compute the probabilities of each. Okay, so PDF of X for the range 2, 3, 4, 5. I'm not using ... here because we're going to do a computation. Okay, so all the numbers 1 through 12 listed out there. And each of those has a probability. We're going to multiply these results with their probability and add them all up. Okay, that's what the formula tells us to do anyway. Okay, so 7 is the most likely, right? That's 6 out of 36. And then each one on either side of it goes down by a 36th. There are 5 ways to roll an 8 or a 6. There are 4 ways to roll a 5 or a 9. 3 ways to roll a 10 or a 4. 2 to roll a 3 or a 11. And 1 out of 36 for 2 or 12. Okay, so the reason we're doing this is we're going to apply the formula, just the base formula. Okay, which is the weighted average over the range of values of the value that you get times the probability that it's equal to that value. And all of these products here, you take 2 times 1 over 36, 3 times 2 over 36, 4, all these things are going to be over 36. Okay, so we're going to add them all up. We're going to form a numerator over 36. Now, how many 36 do we get? Well, 2 times 1 is 2, 2 times 3 is 6, 3 times 4 is 12, 20, 30. Sort of look like triangular numbers, but then it sort of breaks the pattern after 7, because this thing starts counting down. 5 times 8 is 40, 9 times 4 is 36, 30, 22, and 12. Okay, and then we add all these things up, right? So let's do it. So 2 plus 6 plus 12 is 20. And we got another 20 and 30. That's 70, 112, 152. Plus 36 is 188. 218 and 22 is 240 and 12 is 252. Is that right? Some of you are nodding, which is giving me confidence. That's good, because I need it right now. My adding is not so good. Well, let's just see. That looks good right away. The 252 is divisible by 9. So the 9 will cancel out. Let's see what else we got here. And a 4 should cancel out too. Oh, this is actually a multiple of 36. That's really good. Okay, so it looks like it's 736. That was some sweat. Okay, and you should never do this. You should never do this. Why? Well, because last time we developed this thing. Okay, that expectation is a linear operator. Okay, so if you have some variable that you add together, 2 little variables, you can just add their expectations together and get a result. That's what we're going to use here. The other is if you do a scalar multiple, you can just pull the scalar multiple out. Somebody wrote in to tell me that I had a typo on the very last line here, and I apologize for that. They are absolutely correct. This C got dropped, so if you want to just add in a C there, that will make things right. But anyway, linearity of expectation is your friend, and you're going to use it a lot. It's going to solve a lot of problems for you in a much more efficient way than what we just went through. I mean, that was pretty painful. Okay, so let's look at the better solution. All right, what's the better solution? So solution better. They're both solutions. Anyway, use linearity. Okay, so what I mean? Well, we want to find the expected value of x. X is equal to x1 plus x2, so that's equal to the expected value of x1 plus x2. And because of linearity, that's equal to the expectation of x1 plus the expectation of x2. And we know what the expectation of one die is. We computed that earlier, right? So the average roll that you get is 3.5. Okay, so that's something that we did earlier. And that's equal to 7. Yeah, we're going to do a fair number of examples today that apply linearity. Okay, and you should use linearity whenever you can. Now, just some notes about linearity. It only works on the plus operator and the scalar multiple operator. It doesn't work in general on like multiplying two variables together. Okay, so I'll make a note about this later, but it only works on those two cases. That's a good number of cases to work on. Okay, so it solves a lot of the problems that we encounter, which is good. Okay, next problem. Okay, so you play a card matching game, and there are two variations of this where you shuffle the cards, and then you predict what the next card is going to be. And if you're right, then you score a point. And you keep on turning over cards until the deck is done, and how many matches do you expect to get? Now, there are two strategies that you can employ. One uses memory, and the other one doesn't. Okay, and maybe you're smart, maybe you're a good card counter, you've memorized the deck as it comes out one at a time. Maybe you're not, maybe you just kind of want to have some fun and pick random cards. Okay, so pick random cards is the is strategy A. Okay, so you just pick a, you have a 1 in 52 chance or a 1 over n chance in the n deck of cards case. What do you do? Okay, well, we're going to start using indicators to solve problems, okay? So the initial strategy here is we're going to let x of I be the indicator variable. It's either a 0 or a 1, depending on whether you're unsuccessful or successful. It's equal to 1 if you are successful, okay? That will total up into a variable, basically, where you're, it's sort of like you're writing a computer program that, increments this x every time that you're right, okay? So you just say x is the sum of x1 through xn, and that's the total number of matches, and you ask yourself, what is the expectation of x? And the solution, the hard work, if there's any hard work to be done, is to write out x1, x2, xn in this bracket, and then use linearity on that. Okay, so it ends up being the sum of the expectation of x1 with the expectation of x2, the expectation of xn. Okay, so sorry, I should start color coding these things again. Okay, so again by linearity. All we have to do is figure out what the expectation of x1 is, or x2 is, down the line. Okay, so that's the $1 million question. It's not really a tough question, right? What is the expectation of x of I? What is it? Is that 1 over 52? Yeah. Okay, so you take a stab at it, and you have a 1 in 52 chance, 1 in n chance in the n card case, right? Okay, and you can think of each of these indicators, they're Bernoulli's, right? Where the probability of it being 1 is the probability of the event coming true, right? It's not a very big chance, but it is a chance. Okay, so E of xi is the probability of xi equal 1. That means the probability that you're going to be successful, and you take a guess with uniform probability. So that's 1 over n. So each of these things ends up giving you 1 over n. So the expectation of x is 1 over n plus 1 over n plus 1 over n. And there are n of them. And that gives you 1. Okay, so on average, you expect to get one question right, one guess right, if you just stand in the dark. Yeah? Feels about right. Yeah, so the deck, once like the ace of hearts is gone, it's not going to be guessed again, but we're not remembering the ace of hearts is gone. Okay, so it might be that later on, after the ace of hearts has already been drawn, we guess the ace of hearts. Which doesn't make much sense, but maybe our memory isn't that good. Okay, so we're going to look at the next case where our memory is good. In fact, our memory is perfect, and we employ sort of not a perfect strategy, but a better strategy. Okay, but I grant you, if you say ace of hearts and the ace of hearts are already gone, the chances that you get it right are 0. But you're the one that's making the random guess, not the deck. Yeah. No? Okay, other questions? Yeah. Okay, so let's look at the memory case. Okay, so same question, but you're allowed to remember exactly what's been turned over. You might guess the same thing more than once, but you're not allowed to guess a card that has already appeared. Okay, so you get the first one right or wrong, you don't guess that card ever again. Okay, so same sort of start to this. We define x as before. It's a bunch of indicators at turn 1 for x1, turn 2 for x2, all the way to turn n for xn. But the probability changes, right? Like near the end, your probability is pretty good, right? Like the last card, what's your probability for the last card? It's 1, right? It's 100%. You're going to get it right, assuming you haven't messed up, right? And the probability on the last card, second to last card, it's a half, right? Okay, so the probability is going to get better and better as the game goes on. Okay, so solution. This time, the expectation of the ith guess, the probability that your ith guess is correct, is what? Good, yeah, how'd you get that? Good. So you need something that is going to go down over time, right? Okay, on the denominator. It's definitely going to be 1 over something, whatever the number of cards left in the deck is. But yeah, it's got to start off on the first guess as being, n minus 0. It's going to be a 1 over n chance. Okay, and to see that this thing lines up, remember the probability that x1 is 1 is 1 over n, right? And the denominator should go down by 1 each time, so 1 over n minus 1, 1 over n minus 2, and so on. So I guess it's xn minus 1 equals 1 is half, and the probability xn equals 1 is 1. Okay, so that fits that. You might be off by 1 if you said, n minus I, but again, it starts at a 1 index, so that's why we have to, I think you said I plus 1. I think you expanded the bracket, right? But anyway, yeah? Everyone agree? Okay, so the expectation of x this time is, well, it's, we use linearity, and then fill in the blank for this thing, right? So this ends up giving us 1 over n, plus 1 over n minus 1, plus 1 over n minus 2, plus 1/3, plus 1/2, plus 1. What is this number? You seen this before? Do you remember? Where have you seen it before? Say it louder. It's not n times n plus 1 over 2. That would be if you added 1 plus 2 plus 3 plus all the way up to n minus 1. These are fractions. Yeah, so it's a little bit different. No, it's not quite. No, it's not that. I'm not going to repeat that. Sorry. It's not n times n minus 1 over 2. It has nothing to do with that. Where have you seen it? Or is that the same answer? Remember, they're calculus. It's a harmonic sequence, right? Okay, so you remember you take the, I'm going to show the integral picture of this, okay, but if you integrate 1 over n, and just take the integer blocks underneath the curve, you end up getting this sequence, right? 1 plus 1/2 plus 1/3 all the way up to 1 over n. This thing diverges. It goes to infinity. There's an infinite amount of area. But if you take it all the way up to just a stopping point, this thing ends up being approximately, the growth is, it follows the integral of that curve, and that's close to the natural log then. Okay. More on that for another time, though. Okay, kind of cool, right? First time we've seen a log appear for something. I don't know what the natural log of 52 is off the top of my head, but it's a little less, the natural log, or the e is less than 3, a little less than 3. 3 to the 4 is around 81, and 3 to the 3 is around 27. So I suspect it's somewhere between 3 and 4, maybe 3.5. 3.95, so it's pretty close to 4. So you expect to get 4 things right if you use perfect memory. Yeah, that's cool. Yeah, let's add that in there. Thank you. I like that. Okay, good. All right, we're going to do a little bit more with this linearity thing, but this is a very powerful tool, and you're going to use it a lot. At least you should think about using it when you're faced with a problem. Okay, a little review time. Catch our breath. Okay, so the expectation of a random variable is sort of a product of its value with its probability. Okay, so it's a weighted average. It is a true average for uniform distribution, but for other things, it is literally weighted. There are 2 definitions. One follows the PDF, and that's the one we tend to use a lot more. We did use this in proof. Okay, so and this deals with the sample space. Okay, so we tend not to see much about the sample space going forward, but you can do it using the sample space. Now, making more complex random variables is going to be our bread and butter going forward as well, and you can do anything you want that you would normally do with any function. You can multiply, square, add, multiply by a constant, do 1 over, whatever. You can do whatever you want. But if you do something special, if you do either of these 2 things, okay, so you add 2 random variables together or multiply a random variable by a constant, linearity applies. And it's a very handy tool. It does not apply in general for other things. Okay, it doesn't apply for other things. So it applies in this case and in this case. Okay, but not the other ones that are listed there. Okay, so if you took the expected value of x times y, you can't multiply their expected values together in general. We will eventually prove that you can do this if they're independent. Okay, but we haven't talked about what independence means for random variables yet either. So, but if they're independent, you can actually get this. Or 1 over z, it's not 1 over the expected value. Okay. Okay, so it doesn't work in all cases, but you know, a lot of the time we sum up a bunch of variables to, you know, break down the large problem into smaller problems, just like we did with the card matching, and linearity will be the tool of choice. Okay, speaking of which, let's do binomial. Yeah? Okay, so binomial distribution, you toss n coins independently, they're weighted coins, and you total up the number of times you get heads. Okay, this is equivalent to doing n independent Bernoulli trials. Okay, so that's another way of looking at this problem. It turns out to be a very handy way of looking at this problem. All right, there are two ways of computing the expected value of R. One is by using first principles. Okay, so R, you can have anything, and it might be worth it for you to do this, right? Because we did this for geometric, and we experienced a little bit of resistance, a little bit of pain, right? Dealing with that weird sum. And I'll go back to that slide a little bit later today, just to shore up some things that are interesting and perhaps new. But you can do the same thing for binomial, right? You look at the range. You can have anywhere between 1 and n heads. And the PDF, so the probability that R is equal to x, is equal to n choose x, p to the x, 1 minus p to the n minus x. Okay, and then you try all the things, right? You combine this range with this PDF, right? And you put it into the expected value formula. Okay, so it's the sum from, might as well keep using x. X is equal to 0 up to n of, okay, so we take the weight of this, that's the range, so it's x. Okay, let's get rid of that x. So that x comes from up here, times the probability distribution function, and choose x, p to the x, 1 minus p to the n minus x. Okay, so that bit came here. And yeah, this sort of looks like a binomial theorem, right? Sort of looks like it. If that x wasn't there, you would have the binomial theorem, sum to 1, but that x adds some complication, just like it added some complication for the geometric. Okay. I mean, it depends on what you think pain is. Okay, some of you might enjoy it. I think one of the other sections of Compute 210, like in past semesters, has this assigned as one of their assignment problems, is to do the algebra for this. And maybe it's instructive to do the algebra. I don't know. I mean, if you look at the binomial theorem, you can maybe figure out what to do. Like you say, I equals 0 to n of n choose I, x to the n, sorry, I should not put a bracket there anyway, y to the x minus n, sorry, n minus x. Okay, and this is pretty close to this. And, you know, maybe you see a little bit of creativity at play here, right? Sorry, that should be, I put in n, so I meant to put in, that's why I got confused. That's xi, that's I. Okay, and you sort of want this, this coefficient, you want this power to be out front. And there is a way to get that power to be out front, and that might, you might say, okay, I can take this I and get it out front by taking the derivative. You sort of imagine that I is gonna be there by taking the derivative with respect to x. And you take the derivative of both sides, that'll lower the power, then you multiply both sides by x. Okay, so that's more or less what needs to be done to make this thing work, and you can do it. Okay. Incidentally, somebody asked a question when we were solving this thing last time. Let's just quickly go back to this. They had a solution or some closed form for this thing, and I didn't quite understand what they meant while we were doing the class. And they came down and they also had a derivative trick, and I think it's worth sharing. I mean, maybe it's not, but it's kind of cool. So I like seeing cool math, and maybe you like seeing cool math too. So you can take the sum. Let's make sure I got this right here. I didn't write it down. Sum from I equals 0 to infinity of r to the I is equal to 1 minus r. And then if you take the derivative of this, then you get this, this I comes down. Okay, so you end up with I times r to the I minus 1. So sum of that, I didn't leave myself enough room there. And then you take the derivative of this thing, and that ends up being 1 over 1 minus r all squared. And that's what he was trying to tell me during class. This thing looks smashingly like this thing. And so maybe you could just sub in, 1 minus p all squared for that. And so yeah, that's where he got it from. You just sort of saw that, and that's kind of cool. You take the derivative, and maybe that's a trick you like to use, and that would certainly have simplified our life a little bit here. Maybe you don't know tricks though. Okay, so maybe you could do this anyway. Thought I'd share that with you. Anyway, back to this. We can avoid the painful algebra by just using linearity. All right, so let's do that. use linearity is by breaking it up into its n independent Bernoulli trials. Remember, it's a coin flip each time. We total up the number of successful coin flips. We can do the same thing that we did in the card counting example. Okay, so remember, there are n independent, doesn't really matter, but n trials. So let R sub I be the result of the ith Bernoulli trial. Okay, and what's R? Well, R is R1 plus R2 plus Rn, right? So you add them all up. And maybe I shouldn't be using the dot, dot, dot. I don't know. It looks a little easier on the eyes, but if you want to use sums, maybe we should try that out, give that a whirl. Anyway, it doesn't really matter. Okay, so the expected value of R is the expected value of the sum from I equals 1 to n of R sub I. Okay, so that's R1 plus R2 plus R3, all the way up to Rn. And by linearity, that's equal to the sum from I equals 1 to n of the expected value of Ri. Okay, and we know the expectation of a Bernoulli variable. What's the expectation? It's p. Yeah. Okay, so the expectation is p. So we have the sum from I equals 1 to n of p, and that's just a constant. So we're adding p to itself n times. So that's np. Okay, so if you do a weighted coin flip, okay, it's weighted by probability p, n times, your expectation is n times p. This sort of follows our intuition a little bit, but that's actually some formalism for that. Okay. Questions about the derivation? Is it example time? Okay, so we're bringing back the screw example, but we're putting a little bit of a twist on it. Okay, so just to remind you what's going on. So the screws produced by a company are defective at a rate of 1%. So it's independently 1%. The company sells screws in packages of 20. And they now are proposing a policy where every defective screw will get not just the money back, but the company will pay the whoever it is $2 per screw. Okay, so how much money are they expected to put out for this? Okay, well, let's give this a try. Yeah. Okay, so we're interested in a bunch of things, right? We're interested in how many screws are defective per package, I guess, on average, and it's going to cost us $2 per defective screw, right? And you can blend those two things together if you want, okay, and make a complex random variable. We're not using complex numbers; I don't mean to make it sound that way. But really, we're looking at this binomial distribution. How many defective screws are we going to get per package? That's really the question we want on average. Okay, so let x be the number of defective screws per package. Then x has a distribution of what? Okay, someone other than you and you. You guys answer like 90% of the questions. X behaves like? Good. Okay, binomial of 20 and 0.01. N is 20 things per package, and 1% chance for each. Okay, we could ask the question, what's the expected number of screws per package, and multiply by 2. Or we could, introduce another random variable. I'm going to do that because, you should get in the habit of doing this too. So we can introduce another random variable, y. Y is the amount of money. Y is going to be equal to $2 times the number of defective screws per package. Okay, and it seems like I've made life more complicated, but really the math is no more complicated when we get to the calculation. So you'll see in a second. Okay, so that's the setup. And we're trying to compute the expected value of y. Okay, let's do it. So y is equal to 2x. And what happens next? Pull out the 2. Why? Linearity. Good. And what happens next? Okay, so we're going to use the result of the previous slide. Expected value of x is n times p, n is 20, p is 0.1, so 20.01. And that gives us 40 cents. All right, how does it feel? Pretty good? Okay, questions? Okay, good. All right, so let's do one more. I don't have an example for the Poisson, but I think it's a good thing for us to do another expected value computation. And yeah. What else was I going to do today? Yeah, let's do Poisson. Okay, so recall that the Poisson distribution has this PDF. And what's the expected value of R with a Poisson parameter of lambda? Lambda, remember, is the load factor. It's the average amount of stuff per bin. Let's give it a try. There's no fancy thing that I can write out a bunch of intermediate variables and apply linearity. This one is going to require a little bit of sweat. Okay, so it is the sum, the infinite sum from I equals 0 to infinity of I times this. E to the minus lambda, lambda to the I over I factorial. Okay, a couple things to note. When I equals 0, this thing is 0, right? Because you're multiplying by 0. That's not very exciting. So we could start this sum from 1. Another thing to note, when I is 1 or greater, this I will cancel out the first term of this I factorial and leave us with I minus 1 factorial on the denominator. Okay, so let's write that out. So this is the sum from I equals 1 to infinity of e to the minus lambda, lambda to the I over I minus 1 factorial. Now, because I sort of know where this is going, I know what to do next, but I just want you to see what is sort of the goal here. Well, first, this has no dependency on I, so we're just going to pull that out as a common factor. That's an easy thing. And we're going to be left with lambda to the I over a factorial. And, that looks like the Taylor series expansion for like e to the something, right? E to the lambda. Except that there's one extra thing in the numerator. Okay? It doesn't quite match up. The power in the numerator has to match the factorial in the denominator. Okay, so this is off by 1. So really, what we're also going to do is we're going to pull out a lambda. Okay, so to make the power and the factorial match. Okay, so we pull out a lambda, we pull out e to the minus lambda, and the thing that we're left with is the sum from I equals 1 to infinity of lambda to the I minus 1 factorial. And if you try looking at what's going in the sum, right? I equals 1, that will have, lambda to the 0 divided by 0 factorial. And then I equals 2 will be lambda to the 1 over 1 factorial, lambda to the 2 over 2 factorial, 3 over 3 factorial, and so on. Okay, so our last step here is not really a step, but it's re-indexing this thing, so it starts from 0, and that'll give us our nice Taylor series back. Okay, it's not really a step. We could maybe skip this step if we were so inclined, but anyway, so count from 0 instead, lambda to the I over I factorial. This bit, of course, is our Taylor series for e to the lambda, right? Okay, so that gives us lambda times e to the minus lambda times e to the lambda. And those two things wash away, and we get lambda. Which seems almost magical, right? Like, of all the things you would expect to come out of this, was it lambda? And the answer is it should have been. Why do I say that? Well, remember, lambda is the average load, right? Lambda is the average. That is the parameter that is in the Poisson. So lambda as the average makes sense as a sanity check. Actually makes a lot of sense that the computation works that way. Okay. So note, this passes the sanity check that lambda, which equals n over m, is the average load per bin. Okay, so that's the average as defined by the distribution, and it ends up being the average in the result. It's pretty cool, right? Okay, but the math, like, this looks like weird math, like it was, wow, it's lambda, but it actually agrees with intuition. It's cool. Okay, good? you look sad. I don't want you to be sad. I have a really cool thing to show you, but I'll take a question first. Yeah. Lambda is a parameter that describes remember it's a balls and bins sort of problem. So you have n balls that go into m bins. So the average load per bin when you just toss the balls into the bins randomly is n over m, right? Necessarily, because there are n of them divided into m, right? So by average. So that's what lambda is, our parameter, is our load factor. And yeah, it uses the word, I mean, it is the average, right? Okay, I have one more cool thing to show. I couldn't show it to you initially when we did this because we didn't have linearity, but now that we have linearity, I want to go back to the geometric distribution, and I didn't bring the slide down. Okay, I brought somewhere that I can write because that slide was really congested. I did bring it. That's right, we did it earlier. Okay, so this is a lot of messy math, right? It was a lot of messy math. We got through it, okay, and we got 1 over p as our expected value. Now, because we're computer scientists and now we have linearity of expectation, we can do a trick, and it's a really cool trick, all right? So here's the trick. Okay, first we draw the probability tree. Okay, and it's an infinite tree. You can't, draw it all. Okay, so this is the tree for variable r. Okay, and we want to compute the expected value of r. Okay, so the expected value of r. Now, because oh no, we're missing one piece of this anyway. Okay, we're going to take a weighted average over 2 cases. It's basically what we're doing. Okay, one case with probability p, we finish. Okay, so with probability p, we get a value of 1. Okay, so that's one case. And with probability 1 minus p, we roll again. And because of recursion, this is the exact same tree repeated 1 level lower. Okay, but the value goes up by 1. We actually have to add 1 to this thing. Okay, so if you look at the values on this tree, 1, 2, 3, 4, 5, and so on. Okay, so this is spaced downwards by 1. So this tree here is r plus 1. So with probability of 1 minus p, we are going to get the expected value. I'm writing e twice. That's not what I want. The expected value of r plus 1. And that's a recursively defined formula. But we can solve this formula for e of r. Okay, because linearity will apply to this thing. Yeah, this is cool, right? Okay, all right. So one case was p, got a value of 1. 1 minus p got a value of the same tree spaced 1 level deeper. Okay, let's solve. Let's just solve. This is going to be cool. All right, so this is p. Okay, so this is really expected value of r plus 1. Okay, so we're going to expand that thing out. This is going to be 1 minus p times expected value of r plus 1 minus p times 1. I put the pen cap back on there. Okay, and then I bring out the big red marker. Oh, I love the big red marker. Okay, so let's look and see what's here. P and minus p. Expected value of r cancels with that 1.